Welcome to Linear Programming and Applications. Today we are diving into a fundamental concept in transportation problems, the initial basic feasible solution. Imagine you are managing a bakery with multiple kitchens and storefronts. Before you can find the absolute cheapest delivery routes, you first need a basic plan that simply gets the right amount of bread to the right stores without running out. This starting guess is what we will learn to build today. It is the crucial first step before any optimization can happen. Now that we know what our goal is, let us look at how it works in a transportation model. Why does this concept matter? Because complex computer algorithms cannot start from a blank screen. If a global shipping company wants to minimize fuel costs, their software needs a mathematically sound starting guess. If the starting guess breaks supply or demand rules, the program crashes. An initial basic feasible solution provides this solid foundation. It is simply a valid delivery plan that ensures every factory ships exactly what it produces and every warehouse receives exactly what it needs. Building on that foundation, we need to understand two key terms: feasible and basic. A solution is called feasible if it perfectly balances the books, meaning the total amount shipped out of every factory exactly matches its supply, and the total amount received by every warehouse exactly matches its demand. But to be a basic solution, it must use a very specific number of active shipping routes, which we call allocations. If you use too many routes, the plan contains unnecessary closed loops and is too complex to optimize. We need exactly the right number of routes. This requirement leads us to our first mathematical rule, the supply constraint. Conceptually, this formula ensures that a factory does not ship more than it has, nor does it hoard inventory. The symbol X sub ij represents the amount of goods sent on one specific route, and S sub I is the total supply available at that specific factory. The summation symbol means we add up everything leaving that factory going to all warehouses. If the supply S sub I increases, the factory has more goods to distribute, meaning the individual shipments must also increase to clear the inventory. Just as we constrained the factories, we must also constrain the warehouses. This formula represents the demand constraint. Here, D sub j is the total demand required by a specific warehouse. The summation means we add up all the shipments arriving at that warehouse from all M factories. Simply put, the total amount of goods arriving must exactly match what the customers there ordered. If the demand D sub j decreases, the warehouse needs less, so the factories will reduce the amounts sent to that specific location to avoid overstocking. Now that we have balanced supply and demand, we reach the fundamental condition for a solution to be considered basic. This formula tells us exactly how many active shipping routes we are allowed to use. N represents this required number of routes. The variable M is the total number of factories and N is the total number of warehouses. In plain English, if you add your factories and warehouses together and subtract 1, that is exactly how many routes you must use. If you use fewer routes, the solution is stalled. If you use more, it wastes money. With our formulas established, let us look at how to actually build a starting plan. One of the most straightforward methods is the northwest corner rule. Why do we use this? Because it is incredibly fast and systematic. The rule simply tells us to always start allocating goods to the top left cell of our shipping grid, which is the northwest corner. We completely ignore the shipping costs for now. Our only goal is to satisfy supply and demand step by step, moving right or down as factories empty out or warehouses fill up. Before we move on, let us see this with a concrete example. We are given 3 factories with supplies of 50, 40, and 60 units, and 3 warehouses needing 20, 95, and 35 units. Our first step is always to verify that the total supply equals the total demand. We add up the factory supplies to get 150 units, Then we add up the warehouse demands, which also equals 150 units. Because these numbers match perfectly, we call this a balanced problem, and we can safely proceed to make our first assignment. Continuing with our balanced problem, we make our first allocation in the top left corner. Factory 1 has 50 units, but warehouse 1 only needs 20. We ship the smaller amount, which is 20. Warehouse 1 is now full, but factory 1 still has 30 units left. So we move to the right, to warehouse 2. Warehouse 2 needs a massive 95 units. We ship all 30 remaining units from factory 1. Factory 1 is now completely empty, but warehouse 2 still desperately needs 65 more units. We will need to pull from the next factory. Picking up where we left off, factory 1 is empty, so we move down to factory 2. Factory 2 has 40 units in stock, and warehouse 2 still needs 65. We ship all 40 units from the second factory. Factory 2 is now empty, leaving warehouse 2 still short by 25 units. We move down again to factory 3, which has a large stock of 60 units. We ship exactly 25 units to finally close out warehouse 2's demand. Warehouse 2 is now fully satisfied, leaving factory 3 with 35 units remaining. Now for the final steps of this allocation. We move to the right to the last available route. Factory 3 has exactly 35 units left, and conveniently, warehouse 3 needs exactly 35 units. We ship these final units, perfectly satisfying both simultaneously. Finally, we must verify our work using our basic condition formula. We made exactly 5 distinct shipments. Our formula requires m plus n minus 1 roots, which is 3 plus 3 minus 1 equaling 5. Since our shipments match this required number, we have successfully found a mathematically perfect initial basic feasible solution. Let us look at the visual result of the allocations we just made. This diagram shows our 3x3 shipping grid. On the left, you see our 3 factories, and across the top are 3 warehouses. The numbers on the far right and bottom are our supply and demand limits. Notice the circled numbers inside the grid? These are the 5 shipments we calculated. You can clearly see how the allocations form a staircase pattern, stepping down and to the right as rows and columns are satisfied. This visual confirmation helps ensure no supply or demand was skipped. Now that we understand the northwest corner rule, let us explore a smarter alternative, the least cost method. Why do we need another method? Because while the northwest corner rule is fast, it blindly ignores shipping costs, which can result in a very expensive starting plan. The least cost method, on the other hand, looks at the shipping costs for every single route and always chooses the absolute cheapest available route first. By prioritizing cost from the very beginning, this method provides a significantly cheaper and more efficient starting point for further optimization. Let us apply this cost-saving method to the exact same problem. We scan the entire grid of shipping costs and find that the absolute cheapest route in the entire system is from Factory 2 to Warehouse 1. Factory 2 has 40 units available, and Warehouse 1 needs 20 units. We ship 20 units to fulfill this demand as cheaply as possible. Warehouse 1 is now fully satisfied, leaving Factory 2 with 20 units remaining. We then scan the remaining uncrossed cells to find the next cheapest route, which happens to be from Factory 2 to Warehouse 3. Continuing with our cost-based approach, we allocate to that next cheapest route. Factory 2 has 20 units left, and Warehouse 3 needs 35. We ship the remaining 20 units from this factory. Factory 2 is now completely empty, but Warehouse 3 still needs 15 units. We scan again and find the next cheapest available route is from Factory 3 to Warehouse 3. Factory 3 has 60 units in stock. We ship 15 units to close out this demand. Warehouse 3 is now fully satisfied, leaving Factory 3 with 45 units left. We're almost done. Looking at the few remaining options, the next cheapest route is from Factory 3 to Warehouse 2. We ship all 45 remaining units from Factory 3. Factory 3 is now empty, leaving Warehouse 2 still needing 50 units. The only remaining route left on the entire board is from Factory 1 to Warehouse 2. Factory 1 has exactly 50 units, perfectly clearing the last factory and filling the last warehouse simultaneously. We made exactly 5 shipments, matching our required number of routes. This is a valid and much cheaper starting plan. We have covered a lot of ground today. Let us review the most important ideas. First, an initial basic feasible solution is simply a valid starting plan for a transportation problem, ensuring that all supply and demand limits are perfectly respected. Second, to be mathematically useful for optimization, it must use exactly m plus n minus 1 shipping routes. Finally, we saw 2 ways to build this plan: the northwest corner rule, which is fast and systematic, and the least cost method, which provides a cheaper, more efficient starting point. Mastering these ensures you can set up any complex logistics problem.